This is the IMTS Network, and I'm Travis Egan. Welcome to the third hour of our premiere of the IMTS Network live stream event. In this hour, we will talk about emerging technologies. Emerging technologies are the groundbreaking innovations that disrupt the way we live, the way we work, and the way we manufacture. Examples of transformative technology include additive manufacturing, artificial intelligence, machine learning, robotics and automation, and digital manufacturing. To highlight these emerging technologies, the AMT hosts the Emerging Technologies Center at IMTS. This is to inform and excite manufacturers about the future of manufacturing technology. The ETC is the first place that we featured industrial 3D printing, voice-activated machining, and digitally connected robot-operated machine cells. AMT is also launching a new event. This event is about transformative technologies and will take place in the heart of Silicon Valley in 2020. This event, MT360, is the convergence of manufacturing and technology. Coming up, you'll see some short episodes on emerging technologies in the industry, including digital manufacturing, industrial automation from our guest contributor, the MFG Tribe's visit to Concept Systems Incorporated, the incredible advances in manufacturing synthetic silk, and this is an original IMTS network production called Tech Peak. Also, machine connectivity with the IMTS network's very own Jules McGuire and MTConnect's Russ Waddell will talk about how to standardize factory device data. So up next, AMT's Chief Technology Officer, Tim Shinbara, will speak with Tom Kurfess. Tom is a scientist at the U.S. Department of Energy's Oak Ridge National Laboratory, where he works daily applying emerging technologies to manufacturing applications.
Hey folks, Tim Shinbara here with the IMTS Network. I'm the VP and Chief Technology Officer at AMT, the Association for Manufacturing Technology. We're going to talk a little tech for a bit with my good friend Tom Kurfess. Tom, why don't you introduce yourself to everybody?
Hey, sure, no problem, Tim. So I'm Tom Kurfess. I'm the Chief Manufacturing Officer here at Oak Ridge National Laboratories in Oak Ridge, Tennessee.
Fair enough. A lot of chiefs going around in this area, man. Welcome to the club. Hey, tell me a little bit. You got some new digs there at the manufacturing demonstration facility. Tell me a little bit about what you've seen differently in the last year or so in the manufacturing world and what your role is there at the MDF versus professors.
Sure. Well, so just a little bit of background. Of course, I came from Georgia Tech, where I was on the faculty in mechanical engineering, and I joined Oak Ridge National Laboratories back in January of this year, so January 2019. And really what we're looking at over here is how do we take the latest and greatest technology and rapidly ramp it up, scale it up, out into manufacturing operations. So we've got some great things happening, of course, over at our different universities and our different institutes and so forth, and actually throughout, whether it's innovation in small companies or federal government or even large companies. What we're all about here is taking some of those innovations and scaling them up and getting them out into production, both process and product.
Got it. Everyone uses the word advanced manufacturing, which always begs the question, well, what's advanced in manufacturing? I mean, over the last year, what's different in our state of industry as far as advancing the state of manufacturing?
Well, it's a great question, Tim. So, I think we can go into a variety of different areas. Of course, we've got additive manufacturing, sometimes also commonly called printing. We've got IoT, so Internet of Things for manufacturing is really called IoT for MFG. We've got all sorts of connectivity capabilities and so forth, and latest and greatest technology, for example, in machine tools that may actually be on the machining side, but now we're seeing machine tools that have additive or 3D printing type capabilities on them, so we'll call those hybrids. But I think really what we're seeing is we're just seeing a lot of advanced technology working its way out into the manufacturing sector. So what's happening is all of these great ideas are all coming together, and now they're being applied in manufacturing. Simultaneously, and really what's going on is this is happening at an accelerated rate. So you're seeing new technology, and it's getting out there. Instead of taking 10 years or 5 years or even just a few years, people are accelerating those technologies out there into production because, of course, it gives you an advantage over your competition. So you want to get it out there as soon as possible.
Yeah, we totally agree. We've seen it on our side. These two communities of technology, high tech, big tech, if you will, in our manufacturing community, manufacturing technology and distribution areas. And these two communities are starting to bridge, but they're not bridging fast enough. That's one of the things we're doing, trying to get out into the valley and talk MT360 and talk about meetups and talk about the different things that each community didn't know about one another. We're seeing a lot of the startup companies really start to accelerate our industry. People would say disrupt the industry, but I think they're accelerating the industry. I mean, AI, machine learning, certainly on many aspects. I'm starting to see a little bit in the controls world. I mean, in a perfect world for you, what does an advanced control system look like in the 21st century?
Well, I'll tell you, and I think the control is really where it all is going to come together. In the 21st century, of course, we're pretty far in it. We're another couple of months, it'll be 20% through the 21st century, right? So, but the reality is the control is really where it's at, because that provides you, if you think about, IoT, so Internet of Things, this is the controller is linking into it. This is where all your sensors are coming together. I was a graduate student about 35 years ago, and I would spend months putting sensors on a machine tool and so forth, and then I'd make several runs and collect all this, all the data, right, and then analyze it. Well, today, every time we make a pass on a machine tool, all those sensors are there. So we're generating all the data that 35 years ago was a big PhD project. It's now in production. So to me, that next generation controller is gathering the data. That's part of it, and then connecting it to the outside world where we can take a look at models. Is our machine behaving properly? Predictive maintenance. I was just reading some articles today about predictive maintenance. So is the machine doing okay? And if it's not, should we shut it down, or can we have a control shutdown maybe over the weekend when we do some repairs, as opposed to just having the machine break, or even scheduled maintenance where maybe you really don't need it, so it's not very cost effective. So I think it's connecting the information from production, and then actually as an individual part is moving along, I've got information from this part, and when it goes to the next process, that information moves along with that part. So when it finally shows up, let's say I'm making a turbine blade, right? And that turbine blade is going to, let's say, Delta Airlines or Tech Ops down in Atlanta. When that blade shows up, number one, you know exactly how that blade was made. And if we're talking, printing that blade, and we're not quite there yet, but when we talk about printing it, we're going to know the microstructure. We're going to know every, element, of every grain of that blade. So we know that's good. We're going to know where it came from, and we're going to know that it's a genuine blade that belongs in that engine. So it's going to be placed in there in a very secure fashion.
So up to now, a lot of this production data has resided on controller, on the machine. In some cases, you might have a linkage up to a PLC or a SCADA system. How do we get that controller and the horsepower and the intelligence that a controller to date has provided? Do we have to have that on the machine? And if not, how do we get that to the edge, and what might be the benefits?
Well, so I think it's sort of interesting. So you use the key word there, edge, right? So edge, I think people are familiar. You've got cloud systems, and so there's this nebulous cloud out there. And by the way, the reality is that, people are using things like Dropbox or Google Drive that they're very familiar with. That's sort of out in the cloud. Edge would be right at the machine. And then we have what I would call the fog, which is, where the cloud touches the ground. And really, the machine tools or any of the systems coming out today, they have such powerful controllers on them that you say, well, yeah, we can do the processing locally. You actually just also mentioned artificial intelligence. So we've got AI going on. And I look at AI as almost a commodity. I can go out and we've got even high school kids now programming for AI, right? So now here's the real question. That is, the controllers, they probably have the horsepower to pull this off, right? But, if not, well, they can go to the cloud and use processing over in the cloud. So they'll go from edge through fog into cloud, and even in terms of data storage, right? So they may send the data up, through the fog up into the cloud. And really what's going to happen, though, is think about it. And by the way, it happens with computers as well, right? The computer I bought a few years ago, well, maybe it's not powerful enough and fast enough, so I get another one. Well, that's one thing when I buy a $500 or $1,000, PC. But when I've got a $500,000 machine tool, well, you don't just say, well, I'll get rid of that one and get a new one. But what happens now is these controllers are going to be smart enough so that as new algorithms, new capabilities come along, they'll be able to say, oh, I don't have enough power here. I'm just going to go off into the cloud. I mean, it's almost a little retro, but when I was a student, we had terminals, right? We would go off to mainframe computers, and the terminals, they were computers, but they weren't particularly smart. Then we went to PCs and did all local processing. And now really what we're seeing, whether it's on a machine tool or even your PC, right, is it's going off to the cloud and making use of data externally, processing here, processing there, out in the cloud. You really, can't tell the difference, right? And that's really what's going to happen with our manufacturing operations and our controllers. Now, they're great locally, but when they need to reach out, they're going to reach out and make use of the rest of the cloud and all the infrastructure that's out there supporting it.
Yeah, understood. And, sometimes we get challenged when we lay out that architecture, and people will say, what about collisions? What about, and fill in the blank that has very high impacts to latency. We can't have millisecond delays. We can't have so on and so forth. One of the reasons I've heard is that it takes so long to read G code, which brings that back up onto the discussion point. Things like trajectory planning, and there's some other ways by which we won't be so constrained to G code. Tell us two things. One, what does it mean to get away from G code? And two, what are the things you see today in technology that we can get away from G code right now?
So I think number one is, with the G code is just a way to go from your design, if you will, down to controlling the motor, right? The servos on your machine tool. And in fact, if you look at what modern CAM systems will do, they actually break up. I'm going to make a 5-axis move on a turbine blade, machining a turbine blade. It breaks it up into a whole bunch of little GO1s. So it's making a bunch of little straight lines and connecting the dots. And so that has been something that we have been using. And I grew up in the machine shop in the 70s. And, we programmed in G code then. I mean, I think where we're going to start seeing it, and I think we've already started seeing it, is different companies will start to put, put various CAM systems directly on their controller. So is it going to generate G code? No, it'll go right to the servo drives and drive the servo drive. And this is going to give you a whole lot more efficiency in terms of, generating this intermediate G code. Now, that being said, and again, I think I want to make it really clear, we are not going to drive the machine tool from the cloud, in the end, right? I mean, you're going to have your local controller. It's going to drive your machine tool, but you'll have perhaps some trajectory planners and so forth at a much higher level, actually taking a look at, okay, we're going to generate some of the trajectories, or maybe when we have new tool offsets or tool wear, we'll actually analyze those, we'll execute those, and we'll download those, to the machine, let's say in between two parts. So just like you do today, you make a part, maybe you make some measurements, right? You punch those offsets in the machine, and as opposed to the machine locally, crunching and generating, a new set of trajectories there, right? It might be generated in the cloud, then sent over to the machine to execute. So really, you're going to break things up, and again, depending on what kind of power, you're going to need down at the local level, you'll have more computations happening, up at the higher level, up in the cloud and so forth.
Yeah, we've talked about the trajectory planning, and really that covers our CAM side of the world. With generative design helping us advance our state of design on the CAD aspect, and then looking at in situ inspection and the technologies that are brought in to make sure what we planned we actually made and it was correct. That whole linking of those parts together is this digital thread, another buzzword most people hear about, and connecting the data with things like MTConnect certainly is an enabler. Out of CAD, out of CAM, out of the whole computer-aided engineering world, are there certain things that have advanced better than others? And is there a particular lever that we want to pull more than any of those if we wanted digital manufacturing to come to realization faster?
Well, so I think really what we need to do is we need to connect up our machines. And so you mentioned MTConnect. So, communication capability of MTConnect is great. I think we also need to start thinking a little bit differently. So let me talk about, you mentioned generative design. And I think, for those of you out there that are not spun up on generative design, if you think about some of these, I basically say, yeah, here is what my loading is on my part, right? So I basically give a functional description of what I need my part to do. And then the computer actually modifies the geometry of the part, such that, it eliminates, elements of let's say the part that aren't supporting any load, right? And so you get these kind of cool looking, almost, natural type of designs. And I think that a lot of us have seen these types of things. And there we're only looking at geometry, so generative design with geometry. But when you're looking at, let's say, additive systems or hybrid systems, you can actually start to take a look at generative design with varying material characteristics. Let's say we had a couple of different materials. Maybe, let's say we have a material. Let's take a turbine blade, right? So at the root of the turbine blade, there's a lot of stress because it's being pulled while it's spinning up. So you want to have, what I would say is a tougher material down there, right, as opposed to a hard material. But you might like to have a harder material up at the tip, where there could be a lot of wear. So you may instead of just putting two different materials in there, you may functionally grade the material. So I go from this tougher, more compliant material down here that won't fracture, to a much harder material that can fracture, but it's only at the tip where you have lower loads. But again, if you just put two different materials together, they have different thermal coefficients of expansion. When that blade heats up, one's going to expand more than the other, and they tend to pop apart. But if it's functionally graded, okay, then you don't see that happening. Right? And so now we start to bring in not only geometry, but material characteristics and performance specifications. Even cooler, right? Now think about it now. I'm running my 5-axis machining center, and via MTConnect, one of my favorite communication protocols, is, I'm monitoring the spindle power, and you might notice that as, you get to the harder material, your spindle power is going up, which is a good thing because that's what you would expect, right? So that spindle power is going up. Yeah, I'm verifying not only because I've printed the material or I've added the material that way, but when I'm machining it to final shape, I'm also verifying, that I have the right material. Even, or let's say I got, some holes in a part. As I machine over those holes, you can bet your spindle power will drop when you get to the holes because you're not machining as much, right? Again, you can turn around and verify that certain things are in the right location with other information that just flows directly off of something like an MTConnect interface.
Yeah, no, I agree. And I'm seeing data coming into the equation even from the simulation side of the world where up to now we've done a really good job of simulating what the geometry would tell us with physics. But when you start talking additive and you're talking voxel, when you start talking about movement and torque as a requirement and not just flatness and angularity, some of the tools to simulate have been lacking the physics and the kinematics, if you will, of all the rest of that equation. I'm starting to see there's some technology companies like Topology and others that are really understanding the physics and are pouring that into what used to be just GD&T type of an inspection criteria. And I think that's what's going to help us leap and bounds go forward in recognizing the realization of additive manufacturing, doing things like bonded composites where there's a lot of questions on the inspection side. How do you know? Are you sure? So I'm really following that space too. Anything else on the simulation world that you guys are seeing out at the manufacturing demonstration facility?
Sure. I mean, again, back to the controllers and so forth. These controllers are open. You can start to put in information, and I've got machining models or even toolware models. I mean, so for example, once again, we know as the tool gets duller. I mean, we saw this, right, in grinding. When the grinding wheels get dull, you see the power levels go up. It's the same thing on machining. So you watch the power levels go up. You can actually monitor, your toolware just by looking at the, at the power levels. And of course, you have, new systems like tool set stations and so forth that will also verify this. So you have a lot of information coming in that allow you to better understand your process. And again, it's one of these things where at some point in time, we have to run some experiments. I think, like I could, I think in high school, right, everybody did, Hooke's law, F equals KX. You hang a weight on the spring and, you measure the difference, that it deflects. So you can compute that spring constant. You could go up and look at, in a handbook, the coil major diameter and the wire diameter and all this sort of stuff and calculate it that way, but I still need material properties. So at some point in time, you've got to run those experiments. Well, as I said before, every time we run that machine tool, I've got all these sensors, I'm running these experiments. But now the controller can have some of the greatest models, and by the way, I think this is very cool, right? You might say, hey, I'm gonna buy for $1, I'm gonna buy some professor's model and stick it in there, and that's gonna help me to improve my productivity. So you bring it all together, and it's also gonna tell me exactly what's going on with my part. And the data you're taking are going to help to refine the models. So it's this continuous cycle of improvement, and we're going to have some amazing things coming down the road.
Yeah, and I think what we also see is an increase of access for people to play with these tools, whether it's data science and AI with Kaggle, or if it's learning on your own all the way from a Khan Academy to MITx. There's all these different resources and access points that more and more people who aren't in a traditional vertical to help our industry are all coming from all different sides. And it's just, the facet of our diamond's brilliant, and it's a fun thing to watch. You've got the last word. What's the most exciting thing you're looking forward to in 2020 as far as manufacturing goes?
Oh, gosh. Wow. There are so many exciting things out there, and you've only asked me to pick one. I really think that what we're going to see is the augmentation of human capability. People talk about, humans, people are going to be replaced in manufacturing. I hope it. People are just too good, right? You've got great senses. I've got my eyes. I can hear things. If you're burning something, or I could even smell it, right? I challenge a computer with sensors, to figure out when you're burning something up. But I think what I'm excited about is the ability for these new controllers, for things like artificial intelligence, using new sensors to really, and also augmented reality, to improve the capability of the human user, or the human operator. And to me, that's what's going to be exciting. I don't think people are going away. I think people are just going to be getting better, and they're going to be getting more valuable, right? Based on this new technology. So that's really what I'm looking forward to.
I hear you. Well, Tom, as always, it's great to serve on the board with you with the MTConnect Institute. It's great to know you as a friend and as a colleague. Appreciate your time today, everybody. This is Tim Shinbara with the IMTS Network. We'll see you next time.
There are times when we manufacture to achieve a grand vision. SpaceX wants to take us to Mars within 3 years. How do you design and manufacture to make that happen? To make anything happen that's novel, untried, new, and visionary.
Let's go do what we know we can do. There are less boundaries out there than we think they are.
The one big thing in the future of manufacturing is going to be the evolution of machines and intelligence in machines that now start telling us what products to make.
Closing that gap from ideas to reality, from bits to atoms.
I'm a great fan of Steve Jobs' wonderful phrase, if you want to know what the future is, invent the future.
SpaceX, one thing they do really, really well is they basically don't take no for an answer. If there's something not on the shelf or quickly developed that they could use, they develop it themselves in-house.
As market forces shift, manufacturing assumes new roles.
You have to innovate, right, to be able to truly capture a market.
Xometry connects customers needing manufacturing with the best shops and suppliers to do the job.
In order to keep the whole demand side of the global economy going, we have to shrink the time to market, the time of exposure to customer, right? And that's the supplier's responsibility and the purchaser's responsibility. Our software reads, predicts, perceives, if you will, what inefficiencies in production are occurring. The whole point is to take the guesswork out, and it modulates across the supply chain for greatest success.
The weakest link is between design and fabrication. Ideas are plentiful, but taking a design and making it is what's hard.
Manufacturing can't exist by itself. It needs to be supported by design tools, by software systems that operate in an ecosystem around it. These often operate in silos and independently of each other because there's very little communication often.
A lot of that can be alleviated if we can bring that information into a design tool. Then those design tools can be more informed.
Among the most powerful tools are those delivering generative design.
With generative design, the designer starts with goals and constraints, and algorithms synthesize the geometry that solves for those goals and constraints. The algorithms are searching through the design space by reconciling multiple objectives that are often competing. and those solutions populate a space, and the designer is still in the driver's seat. That's where we're going, is trying to minimize the possibility that the designs that have been created can't be made. The computational power that we have available to throw at the problem of design allows us to explore more solutions than we've ever been able to before.
Computing power goes far beyond design tools.
The broadest and the transformational change that's happening in manufacturing today is it's increasingly digital, democratized, and distributed. We're able to put sensors throughout the factory floor to capture data in real time and integrate that with sophisticated modeling and simulation tools with the capability to deal with uncertainty. You can track every part and every process, and you can capture the errors before they propagate.
Which comes close to the full available power of artificial intelligence.
When people are trying to understand the likelihood of anything going on in a shop floor environment, that's where AI is going to come into play. Whatever you're trying to understand in your shop floor environment, there's going to be data collected. AI can be used in any subset of your operation, whether it's collecting data, reporting on it, or doing a predictive model around it. Having a data engineer and data scientist is going to be an integral part of your business in the future.
Can AI-powered machine tools change themselves on the fly to perform new tasks?
The idea is to get to the point where the system reconfigures itself dynamically based on the work that's coming in. Even up to the minute, the system will reconfigure and realign itself to meet those outcomes.
If the part is large enough that requires 2 robots, they can actually self-organize, replan themselves to actually service that machine and load that machine, and then of course then go retest themselves. The idea of the robot being part of, like, say, a team may not inherently be new, but how it actually responds dynamically as a true partner or team member is new.
Machines working together, aware of each other, aware of themselves.
The way we want to make this equipment work together is to allow them to become what we call self-aware or more intelligent, so that the devices themselves will start to collaborate together and the manufacturing processes dynamically.
What that means is the machines that they have capabilities that they are aware of. They know how to announce these capabilities to external agents if and when required, and they know how to connect and augment the capabilities of existing systems if they need to. In the near future, I think it is going to be more of the fact that computers are being fed with so much information that they know how to build fairly accurate models of the real world.
The real world of manufacturing includes an ever-expanding array of new materials, some with highly exotic properties, from macro to nanoscale.
There are a lot of advances that are happening in the materials, for example. Metamaterials, high entropy alloys, all kinds of new advances being made, which are still at the laboratory stage.
Engineered to have properties not found in nature, to bend light, block frequencies, change acoustics, even make things invisible. At Xerox's Palo Alto Research Center, scientists and technologists work side by side with sociologists, ethnologists, and anthropologists. The human factor is crucial, but will advances in automation make the role of humans unnecessary?
I don't think the role of humans is going to diminish by any means. In fact, I think that they are the ones who are going to build or augment the intelligence, augment artificial intelligence, and build something like collaborative intelligence.
One of the things that we're learning in our Industrial Internet Consortium testbeds is what the human component is, because we know it's changing, but we don't know what it looks like in 10 years from now, 20 years from now. The reality is people don't go away.
A few of them have had enormous impact as entrepreneurial pioneers.
When you look at people like Jeff Bezos in Amazon or Richard Branson with Virgin, they see a challenge and they can highly focus on that challenge. Manufacturing needs that big leadership to come from outside of our space potentially. Those type of entrepreneurial mindsets, I think, bridge a lot of the gaps we don't see coming down the manufacturing pipeline, as it raises interest from our manufacturing companies today and the leaders in those companies across the globe, quite honestly, that says, well, we can do that too. In fact, we know better how to do what they just did then.
We can best know the future by creating it through the lofty ambition of inspired leaders and through all our resources now converging in novel ways. Generative design, inspired by nature, augmented and virtual reality, enabling distance collaboration, artificial intelligence, reconfigurable manufacturing for optimum agility, hybrid technology, additive and subtractive in a single machine, metamaterials and high-entropy alloys, all materials and processes digitized, a digital thread throughout a product's life cycle. It's all in a future we can make, a future we will make.
What's up, guys? We're in Albany, Oregon. It's raining, and we're at Concept Systems. Concept Systems is an industrial automation company. Who doesn't love robots? We're gonna take a look inside at how they integrate robots into the food industry, aerospace, and tons of other cool stuff.
I spent 15 years in the manufacturing world, and now I'm on a mission to show people how things are made and excite the youthful generations to get them involved in this amazing industry. This is Manufacturing Tribe TV.
What's up, guys? We're here with Ryan Wasman, the Sales and Marketing Director at Concept Systems. Ryan, what is it that you guys do here, and what are we going to see?
We're an industrial automation company, so you're going to see how we build panels, we build robotic cells. You're going to see lots of cool things that we build for manufacturing.
Cool. Let's go take a look.
So this is our shipping and receiving department. This is where all of everything starts.
Okay, so you guys get all your material in here, where everything from the nuts and the bolts up to the robots come through here?
Yeah.
What works through?
Yeah, so as we go through and design something, then we'll put a bill of materials together. That bill of materials gets sent over to purchasing. They'll go through and start buying everything for that specific project. It comes into this location and gets kitted for that project. And once that kit's built out, then it moves onto the manufacturing floor.
So then even the big robots, do they come in and stay here, or do they, do you guys have to move those into a different location?
So they'll come in here, and once they're here and all the pieces for that project are here, then we'll move it out to, we have a second building where we do a lot of our mechanical builds. And we can see that in a little while.
So do you guys have any robots in the crate still that haven't been put together that we can see?
Yeah, actually we have a robot over here that's actually being set up to get shipped out. So this is a paint robot that we've built a paint platform around.
Oh wow.
Yeah. So this is a paint system, and the claim to fame with this one is it has a really simple, easy to use interface, so we can push programs out via the internet. So we don't even have to be on site to program this robot.
Wow.
So it's helpful for general industry customers that don't know robotics programming.
And so from a robot standpoint, from my knowledge, different axes, different ways to control it. How many axes are on this robot?
This is a 6-axis. The term is 6-axis articulated arm.
Okay, so what does that mean?
So it has the ability, it's a 6-axis robot, but it has the ability to move in 6 degrees of freedom. Okay. So a point in space, it can move in X, Y, Z, and then it can rotate around X, Y, and Z.
I know that you guys don't
manufacture the robots, but with the panels, do you guys do anything with those? Anything custom or make those yourselves?
Yeah, actually, on this in the back, you can't see it, but I've got a good example over there of panels that we build. This has a panel that we've used to integrate the robot controller, the touch panel, and some of the electronics that go into getting the data from the cloud.
Okay. So with the panels, are you guys doing them all from scratch based on the application, or do you guys have a set standard way of doing things?
So, well, we have a set standard way of doing things as far as the methodology goes. We build our panels according to a best practice. But for certain things, we'll have the completely custom design panels. Some customers call us up and say, we need this panel design, or this panel built, and we'll build that panel from their print. We have an entire design group that can design these panels as well.
Very cool. All right, let's check out these panels.
Yeah.
Explain to me what's going on here.
So you can see these panels, these are actually being installed in an environment that needs purged air, that needs, there's no paint on these panels because they're going into an explosion environment. So you can see we've laid out everything in this panel. So we've got drives, we've got transformers, we've got all the wiring relays for this. In this panel, this is a great example of a custom design panel we've built to a specification.
So do you guys, so these things are parts that came in through receiving that you guys don't make, but you guys started with basically a blank box.
Yep.
And built this out and organized all this stuff and assembled it?
Yeah, so based on the customer's requirements, they're gonna tell us, hey, we need to control this thing. It's gonna go in this type of environment, and from that, we'll design it into like this type of enclosure is a different NEMA type enclosure. There's NEMA 4, NEMA 12. So we'll pick that style of enclosure based on the environment it's going into. Okay. We'll make sure that the electronics that are going into it will control it to their specification. And this is all from scratch. So we start with this backplane and it's blank.
Wow.
And we have a design group that will lay out the entire backplane, make sure there's spacing for the components, make sure we take into account heat loads, ambient heat temperatures, so that we're not putting this into a 90-degree environment and it overheats, right?
Yeah, that wouldn't be very good. Right? So what's the range of environments talking to that? What type of environments could these be in?
We've done systems for washdown environments, so like food and beverage typically has to be washdown capable.
Is that where they're hitting it with a hose and cleaners and things like that, or?
Yeah, where it will get wet. It's not meant to be directly water poured onto it, right, but it can survive in a washdown type environment or a clean room type environment. We've done panels for hazardous environments. We've done panels for explosion environments. And then just your regular panel.
So it looks like these are ready to go, because I see some others that are half built and being processed. So are these ready to ship, or what's going on with the location of them?
So these are built, but they're not tested yet. And so they're in this spot and they're open like this for panel checkout. So we go through a whole QC process. We make sure that every single wire is tight. We make sure that everything is in place. And then we've got engineers that will actually come out and plug into the panel. They'll make sure it's working. They'll make sure that it's landing at the customer's site, working, ready to go, ready to be plugged in.
So there's like the final test before it gets packed up and shipped out?
Yes, exactly.
All right, so then we've seen the panels. We saw a raw robot come in. Now, putting those two together, what do you guys have to show where you can see both of those two aspects interacting?
So if we walk over to our Bay 3 of this building, or Building 2, which is a separate building that we do a lot of the system builds, you can see these panels attached to robotic cells and some other things.
Okay. So what types of applications or things do you guys work with the robots?
So we work in a lot of aerospace applications around paint. We work in a lot of smaller general industry paint applications. We've done a lot of assembly applications with robotics. We've done a lot of machine vision guided robotics for some cutting, some deburring solutions.
Okay.
We have some collaborative robots that we've done work with, where somebody's working side by side with the robot next to them without safety in place.
All right, Ryan, so what do we have going on over here? I see a couple robots and some controls.
Yeah, so this is an assembly cell, multiple robots in a small area with an 8-second cycle time, assembling some electronic components. So this is actually a piece of assembly line. The other pieces are actually being built in a different facility in the Charlotte office.
Okay.
So this will connect up with 2 or 3 other pieces to make an entire start to finish assembly line for electronics components.
And I see that these are some smaller robots. I mean, from my experience being in the industry, I've seen ones that are bigger. Do you guys deal with ones that are like our height or above?
Yeah, so we've installed small robots this size and even smaller, up to we've done a 2,400 kilogram payload robot that takes up it needs a 20-foot ceiling just to operate.
Wow. So what do you guys have here that we can see from a size standpoint?
We have a mid-sized robot cell across the street if we wanted to go over there and take a look at that.
Yeah, let's go look at that.
Yeah.
All right, so that's what I'm talking about. Bigger robots, Ryan. What is that?
So that is a FANUC, I believe it's an M710. It's a bin picking system for a customer that wants to put an entire bin of parts in front of the robot, have us find the top pieces that we can pick, and then we're picking them, and then we're doing something with them. And then we return them to the bin comes out.
So then it looks like I see you got 2 sample bins here to mock it up. So they're gonna put a bin of parts in that are all jumbled around.
Yep.
No particular order. The robot's got to figure out location of the parts, and then are they going to stack them in the other bin neatly?
It's going to stack them in the bin neatly after that, correct.
So what type of industry is that working for?
So this is actually for a customer that's making, let's see if I can describe this properly, right? They're making metal components for oil and gas.
Okay.
And they're making these pieces, and then they need to do something with them after they make them. There's a secondary process that they need to go through.
Okay.
And that's what this cell's doing. This cell's taking the made piece, finding it in the bin, taking it to the secondary process, processing it, and then stacking it nicely in the outfeed bin.
So what's with the black box and the lens on top?
So that is actually the bin picking solution that FANUC offers. So it's a projector in the middle. The big box is actually a projector. There's a camera imaging it at an angle. So we project a pattern onto the parts that are in the bin, and then the camera images it and finds, based on that shape that distorts when it projects, finds the top pieces. So that's the solution that's helping us actually pick the bin.
So that's looking at the parts and doing that part, and then the robot's taking that information and then determining where it needs to go from there.
Yeah, exactly. Okay. Exactly. These guys are actually working on it over here.
And how fast would this, once this solution is done, how many parts is it turning through? Is it going slow, or is it going relatively speedy?
It's probably a part every few minutes. I don't know the exact cycle time of this, but it's able to bin pick relatively quick, within a few seconds.
Okay.
And then that part has to go to the secondary process that takes a minute or so. And then it's going to put that part in the bin.
Ryan, what's with the giant doghouse looking parts over here?
Let's go take a look. I'll show you what they do.
You can fit inside of them.
They're essentially automated scrap weighing systems. So we have a customer that wants to maintain traceability for their scrap, because they actually get money for their scrap when they ship it. Okay. They want to be able to track it. So these are actually installed where a customer's employee can badge into this, dump their scrap, and it actually records by employee who's putting what scrap into the bin.
So are these turned up? So is this the bottom of it, and it gets flipped up and it goes in?
No. This is the top. They'll actually dump through the bigger slot.
Through the port?
Yeah, right here.
I mean, that's got to be. I mean, weighing scrap has got to be extremely important to those companies, right? Because they're trying to recoup that cost of the material. So you guys got to be very accurate with this, or how does that work?
Yeah, they want to be accurate to within a few tenths of a pound. Mm-hmm. But really, it's when they're shipping their entire scrap out, and they're talking thousands of pounds of scrap. You know, every pound or two can matter, and so if they're not capturing that, and it gets to the scrap people, they say, well, you sent us 2,000 pounds. They say, no, we sent you 2,500 pounds. Now there's this big discrepancy.
Yeah.
So this eliminates that discrepancy for them.
All right, guys, so Ryan has to go. He literally is going to Africa tomorrow. So Ryan, I appreciate you walking us through this.
Yeah, man.
We're going to stick around and show you guys some more stuff. But what's with the trip to Africa tomorrow?
Actually going on a mission trip, going to meet kids that we sponsor in Rwanda.
Very cool.
Yeah.
Very cool. Well, hey,
yeah, be
safe
gone
travels,
for
man.
a while.
I appreciate
Thanks.
you showing us everything. Like
Looking
I said,
forward to it.
We're going to go jump into some things while he's gone and poke around and show some more cool stuff.
Well, my name is Michael Gurney. I'm President and CEO of Concept Systems. I've been with the company since the beginning, 20 years. I was always a tinkerer growing up, so I was the kid that was taking things apart and putting it back together, and hopefully it worked.
So my name is Ryan Wasmond, Sales and Marketing Director at Concept Systems. I've been here for about 2.5 years. I actually got started in manufacturing when I was in my late teens, early 20s. I worked at a design company doing computer science work. I was IT administrator for a design company in Michigan, and the owner of that design company actually told me that I should go visit one of his friends who had a robot that they were trying to program, and his exact words were, "Do you like playing video games?" And I said, "Yeah, I love playing video games." And he said, "This is like playing video games, but in real life."
My name is Michael Jeffers. I'm a panel shop technician. Been here for about 9 months now. Yes, I got started for manufacturing pretty much when a buddy of mine noticed that I had an interest in technology.
My name is Jerry Flynn. My title is Principal Engineer, and I have been with Concept Systems for 6 years. What I like about the manufacturing industry are the many different challenges and opportunities to see different things and see how they work and see how they're made, and it just gives me a new appreciation when I go places and I see things and I know, hey, I know how that was done, or oh, that came off one of my machines. It's just a good feeling.
My name is Evan Gonerman. I am a controls engineer here at Concept Systems, and I've been here a year. I was really into math. My dad was a math teacher for 30 years, so I really just liked math, and that brought me to mechanical engineering. And then it was kind of in college that I started working with robotics and kind of, automation in general, and that's when I kind of started to see, like, this is where the fun's at. this is where the good times are.
My name's Mariah Biederman. I am a software engineer here, and I've been here for 2 years. For robotics, I really like what they enable us to do that we wouldn't otherwise be able to do. I think robots are fascinating because in trying to improve and perfect them, we essentially are looking at how to kind of reproduce and recreate ourselves, things that we understand, like sensing and manipulating things, like using your arms and maneuvering around things and getting things done. So we're trying to have this like introspective definition, we're trying to look introspectively and think about how we do things and then trying to recreate that with some engineering device and producing that in a way to make our entire society more effective and moving it forward.
The reason I've stuck with it is just the constant problem solving. I love puzzles. I love challenges and overcoming those challenges, and so that's been really rewarding to see somebody tell you it can't be done, and then you do it, and then it's done, and it's fun for me to look, we did it. What else can we do?
You don't get worn out here because you're always doing new things. You're always seeing different manufacturing processes rather than the same thing over and over and over and over.
What does it for me is just the ability to create something with my hands and see it as a finished product, and just see something that I built be utilized. It's really, it's rewarding.
There's something fun about walking into a facility and literally seeing how something is made. I've walked through castings facilities, watching them pour liquid metal into ceramic crucibles and turn that into a part that goes on an airplane. Or I've seen big pieces of metal heated up in a furnace and smushed into a shape, and ultimately that thing turns into this really, it was a piece of metal and now it's this spool that goes into a jet engine. I've been in facilities where they make glass bottles, to see the millions and millions of glass bottles being made, and just understanding that the broad impact manufacturing has across the entire world is pretty cool, I'd say.
You will be able to have a hand in so many different industries and seeing how things work, what works, what doesn't work. And it really just offers a jumping off point for along the line, if you find something that you're like, I really am interested in this certain industry, you have a hand in it, and that's pretty rare.
It's the future, right? But it's the present, actually. I think that's some of the coolest aspect of robotics, is that for so long, I think it's been this thing of the future, this sort of, unknown, futuristic thing, but it's really, it's right here and right now, happening all around us. It's like being able to control a toy. Like sometimes I'm working with some of these machines and I feel like a little kid, because I'm like, oh look, the thing moved. I pressed the button and it worked. And it's like super exciting because it's this tiny little thing, but you can make a lot happen. You can, just with these tiny little bits of control, you can actuate stuff that just kind of blows your mind, It makes me feel like a kid.
If you like to build things, why not get paid for it?
Yeah.
When you look at manufacturing in the U.S., there's automotive, there's aerospace, there's food processing, there's metals and mining. The variety is tremendous, and applying technology with the pace that technology is advancing, the growth potential is exponential when you combine those two.
I think there's a lot of opportunity for you to get on the floor and build a machine, to program a machine, to help make things that make the world go.
So this really just gives an opportunity for continuous growth, and it's really just up to you how far you want to go.
I had a 2-year degree in computer science, and I got that opportunity to start programming robots. That led me down a path of being a problem solver, being on the manufacturing floor. I'm in an executive role now, helping manage this company. I don't have an MBA. I have the technical skills that's required to help solve these problems. And so, you could literally start from a 2-year degree and just working towards doing a great job, solving problems. You can move into a position where you're now affecting 100 people helping solve problems.
One of the big things I see today that I think basically all kids that are in it and interested in it is the first robotics stuff, and a lot of the robotics competitions that go on today. Anyone involved in any of that, I think going into a manufacturing or engineering position is just secondhand. They're doing it for fun right now. They enjoy working with motors and robots and things along of that nature, and it fits right in hand with what they could be doing daily when they go to work.
So it's a very exciting field, a lot of variety and a lot of room for growth, and job security long term. It's not going anywhere.
All right, guys, so hopefully you got some value out of that. We saw industrial automation, how it's applied to the food industry, aerospace. We saw panels being made. We saw some robotic equipment and how everything comes together to make these systems. So hopefully you got some value out of it. If you like this content, hit that like button, share with one person you know, and hit that subscribe, and we'll see you on the next one.
Hi, I'm Jules with the IMTS network, and I'm here with Russ Waddell with the MTConnect Institute, and we're going to talk about digital manufacturing today.
Hi, Jules.
Hi, Russ. What do you do in relation to digital manufacturing?
Well, I'm a standards developer, which means I put together standards. The one I work on is the MTConnect standard, which happens to be a digital manufacturing standard. Essentially, MTConnect itself is a language for all types of different computers and machines to talk to each other. Because it's a machine-to-machine communication standard, that puts it pretty squarely in the digital manufacturing space.
Okay, so talk to us a little bit about the technology landscape that you referenced.
So the technology landscape for MTConnect and for digital manufacturing more generally it's straightforward. Think about the number of computers that are already running production in plants all over the world, and think about the software that's on those computers. Think about the networks that those computers are on. It's not that modern. There's a lot of outdated software. There's a lot of outdated or outmoded networking. A lot of the networks themselves or software are actually just old. Some of that's going to be replaced with new technology. Some of it is going to go away and be retired. Some of it is going to be supplanted or supplemented with new or additional technology. So right now it's kind of an interesting time, and it's been like this for the last, say, 3 to 5 years, where we're really seeing an increasing pace of change in manufacturing that really just comes down to how do you get better networking software in the production process.
Okay, so bring MTConnect into that for us. What is MTConnect at its most base form?
Sure. So MTConnect, like all other data standards in manufacturing, and there's a lot of those, is essentially a piece of the puzzle of interconnectivity, interoperability, and just kind of the plumbing behind how everything works. So if you think about applications in digital manufacturing that are trying to solve some manufacturing problem, maybe that's predicting when a tool will fail. Maybe that's predicting when a spindle will, go out of round and need replacement or repair. Those types of problems where you're taking information or data in, crunching some numbers, applying some algorithms, maybe you're doing some machine learning, big data. These are now kind of into the buzzword territory, but that stuff all needs underlying infrastructure where the data is collected, it's scrubbed, it's normalized, it's transported from place to place. There's a security layer that needs to go in there. MTConnect is one little sliver of that, where we're normalizing definitions for all that data coming out of the factory.
Excellent. So who uses MTConnect?
Sure. So we're focused primarily on discrete manufacturing, which means anyone who's using a CNC machine or anything that's making discrete metal parts, cutting and forming type of processes tend to be where MTConnect is focused, not so much on process manufacturing. And the three kind of categories of users that we see are end user manufacturers, so that's your big automotive, aerospace OEMs and their supply chains. The other category is software companies and integrators. So their job is to sort of bring in a piece of equipment and make it do what it needs to do for one of those OEMs, or layer some software on top of an existing hardware system. The third category is those hardware providers themselves. So that's CNC machine tool builders, sensor manufacturers, PLC manufacturers, control manufacturers. Those are the categories. It's the equipment suppliers, the end users, and the software companies and integrators in the middle.
Okay, that makes perfect sense. So do you have to have an IT person to use MTConnect?
You don't have to have a dedicated IT person. There's really no way to get into a digital manufacturing strategy, and that's what you need to fit MTConnect as a piece of anyway, is that overall digital manufacturing strategy, and you can't really do that without approaching IT. So it might be outsourced IT, it might be a part-time IT person, it might be someone who's most knowledgeable about IT in your manufacturing enterprise. In some cases, it could be a full-blown manufacturing dedicated IT department. Across all of those, what's common is that you have to have a plan for what your business needs are and what your IT capabilities and resources are going to match up together. So yeah, you have to have someone thinking about IT, but no, you don't necessarily have to have a dedicated IT person just for MTConnect or the rest of your digital strategy.
Okay, so give us a few examples of some use cases with digital manufacturing that have been either the most fully developed or some of the most fully commercially available.
Of course. So MTConnect been around for 12 years now. And in the early days, what we saw was the primary use case was machine monitoring or factory floor monitoring. And basically that's looking at statuses, uptime, downtime, maybe some downtime classifications, giving you notice when there's an alarm on a machine or something like that. And that kind of broadly lumps into shop floor monitoring. That's becoming a more mature use case, and at this point, probably the next biggest use case that we're looking at is one layer on top of that. So if you're collecting this data, maybe you're storing it, maybe you're reporting it out to your various business units. The next layer is trying to do something more sophisticated with that, something maybe more predictive. So that's where the analytics layer starts to come in. And that isn't necessarily guaranteed to be manufacturing analytics. That could be some sort of algorithm from another domain that's being applied to a manufacturing process to predict back to tool failure or component failure or machine failure, and get away from this maintenance paradigm where we replace fluids or replace pieces of a machine based on a pre-described schedule, and instead moving to anticipating when something will need to be replaced or repaired.
Got you. So with that being said, can you explain what Industry 4.0 is?
I can explain that Industry 4.0 gets a lot of different definitions from a lot of different places depending on who you're talking to and what you're asking them about. When someone comes to me and says, hey, I'm trying to do Industry 4.0 in my factory and it seems like MTConnect might be a good fit, the first thing I say is, what are you trying to do? And the answer to that, it's not a snarky comment, oh, what are you actually trying to do? It's trying to get to what is your business need for Industry 4.0. So in a practical sense, being able to define it as nothing, in the sense that what I really need to know is what data do you need to collect, what purpose does that need to serve, who are the people that need to consume that data and how in your factory. That's where I take the conversation about what is Industry 4.0.
Okay, so with that being said, how do you get MTConnect?
Oh, getting MTConnect is straightforward. mtconnect.org/documents. That gets you to the standard itself. Like I said, we're a standards developer, so that's going to get you a big, long written document. The thing that most people need when they're going to go start with MTConnect is actually the toolkits and software that go with it. So you can investigate the MTConnect agent, you may be talking to vendors, but most of the information is going to be there on mtconnect.org. You can get everything you need to get started with MTConnect.
Okay, so if your objective is to transition to be a smart factory, and what is the process of getting started? Is it similar to that, or are there some other things you need to take into consideration?
It's planning. And that's not different from trying to do anything in manufacturing where you're implementing new technology. So if you were going to go buy a new machine tool, before you make that investment, you're going to figure out what's the need that it's serving, what are my next best alternatives, what's it going to replace on the floor, or what's it going to supplement on the floor. And you do all that planning in advance before you go and start making any purchase decisions. It's the exact same thing with digital manufacturing, where you need to get really serious about what are the business processes in place that need different data or new data or better data or another source of data. And then after you have those business processes identified, then you get closer to what does the overall infrastructure for that look like? What are the IT requirements? What are the possible vendors that we can be looking at? Or should we be sourcing this internally?
That makes sense. So are you seeing any trends in this space that are kind of popping up? What's the latest you're seeing?
I mean, one interesting trend is kind of around the labor market piece of this, right? So traditionally you have an engineer, maybe you have an operator or a plant type of foreman person, and then you've also got a software engineer, and those three roles have to play together. What we're seeing really in the last year and a half is a significant increase, particularly in new graduates coming out of two-year technical colleges as well as out of four-year engineering schools, is a huge increase in the number of interdisciplinary trained engineer/technicians. So if you're a technician, you have much more understanding of software, networking, all these digital technologies. If you are an engineer, there's more interest in how do I actually connect to a production floor and less of a conceptual engineering knowledge. So I would say that's a trend that's going to impact almost everyone in manufacturing over the next 3 to 5 years. I think it's something that is a really positive trend, and I'd like to see more things happen to kind of continue to encourage that.
That's very interesting. So for MTConnect and MTConnect Institute, what's coming up next?
What we've got next is a version 1.5 release of MTConnect itself. That'll be out before the end of this year. We've recently released an MTConnect OPC UA companion specification. So that takes the MTConnect protocol as well as the OPC protocol and directs on how you would implement those two things together on the shop floor. That's going to get you some extra security layers. That's going to get you some extra assistance if you're going someplace where there's already an OPC install and you want to layer the MTConnect data on top of the OPC system.
Gotcha. So where can people go to find out more?
The best place to go is always going to be mtconnect.org. You can shoot us an email at info@mtconnect.org. You can call me, but I might not answer. So those would be my best bets.
Fair enough, and very honest of you. So thank you so much for your time. And this has been incredibly informative about digital manufacturing and some exciting things that are popping up here. So thank you for joining us. This has been Jules with IMTS Network.